A warm welcome to the World Pipelines podcast. For this episode, I am pleased to be talking to Dr. Samuel Stutz, who is Global Technology Manager for Greene Tweed's composites business. Greene Tweed manufactures high-performance thermoplastics, composites, seals and components, serving clients in oil and gas, chemical and pharmaceutical processing, and a lot of other industries where failure is not an option. Sam leads innovation in advanced materials, and we're going to be talking today about hydrogen pipeline transport. Before I get into that with Sam, here's a message from the team. We're busy planning something exciting. On the 18th of March, I'll be hosting the World Pipelines CCS Forum in London. It's a day dedicated to the CO2 pipeline build-out and how we'll make the UK's carbon capture and storage pipeline networks a reality. We'll cover the engineering challenges specific to CO2 pipelines. We'll outline the different demands for integrity and maintenance. We'll provide project updates from each of the clusters, and we'll debate the future of the sector in the UK. The speaker lineup includes National Gas, United Infrastructure, Eni, SGN, DNV, Penspen, and more. Search World Pipelines CCS Forum for more information. We have special discounted rates for members of pipeline organisations, including the Pipeline Industries Guild, IPLOCA, the CCSA, and UCOPA. Thanks for listening. Let's get back to the episode. Welcome to the podcast, Sam.
Thank you, Elizabeth. Great to be with you.
I want to preface our discussion by saying that for a long time, hydrogen pipelines felt like something that we were talking about in the future tense. Now that they're being funded and built out, we find that a shift has happened whereby industry is having to confront some very practical engineering questions, including how we compress hydrogen efficiently and safely. Sam, can you explain to the podcast listeners why hydrogen compression is such a critical part of hydrogen pipeline infrastructure?
Sure. So I can give it a try. So a pipeline is a very, very, very long tube, essentially. And like the hose that you use to water your garden in summer, it's cold outside now, it's hard to think about it, but like that one, you have an input and you have an output somewhere. Usually it's easy. You can fill a pipeline with gas. You put pressure on it, it stays there, no problem. The trick is to get it moving. So you want to push it from the generator, in that case it would be electrolyzers, down to the consumer, which can be any kind of industry. It can be for car refueling, it can be for steel plants, whatever, whoever is using the hydrogen or any other gas for that matter. And on the way, now when you put up a hole somewhere and you take that out to that industry, well, the pressure drops locally. Obviously, gas will flow in again. And if you have sufficient supply, that will happen all the time. The trick is to get it moving at fast enough pace because there is obviously, due to the length of it, quite some friction, and therefore quite some loss of energy. And you need to resupplement that energy. So if you look closely into pipelines today, we see that there's about every 150 kilometers a repressurizing plant that is just pushing energy back into the system, the energy that was lost due to the friction. And in these plants, there are centrifugal compressors. They need to get a really big throughput. So let's think about the pipeline system that we want to set up in Europe. It's roughly 20 to 40,000 kilometers. So we're talking 140 to 280 different pressurizing stations that need to be built. And all of them, well, we need to be able to compress hydrogen in large volumes, not just a few cubic meters per second, but a few hundred cubic meters of seconds. Otherwise, we'll not get the energy throughput.
The thing that prompted me to invite Greene Tweed onto the podcast was that you have made headlines recently for achieving a record-breaking tip speed with a composite impeller. I'd love to hear more details about that, and if you wouldn't mind starting with the very basics.
Okay, well, let me start with a question to you. Do you know, or have you ever wondered why composites are seen everywhere? Like in bikes, like in aircrafts, in boats, or any other sporting good that you love. Any idea?
Is it because they're light, low weight?
Yeah, low weight. That's one point, but there's more points to it. Any further ideas?
Oh, no further ideas. Enlighten me.
Okay, so it's light, yes, important, but they're also very stiff and extremely strong. So it's the combination of these two things that makes composite very attractive to many places where you indeed do have the combination of weight, which is important, and of strength, which is very important. Sports being obviously the most obvious one, where you want to break your record, you'd better have a very light bike, you'd better have a very light boat, you'd better have a pole vault that brings you up to 6.5 meters, close to, thank you, Mr. Duplantis. So in all of these places, you will see that records were broken once they started to switch materials.
Right, because you're shaving off the difference. You're getting closer to where you want to be.
You have less weight and you still keep the strength and the stiffness of the material. That's where composites are really good. So Greene Tweed does have a very special kind of composite. Well, very special. It's a standard kind of composite that has been discovered or developed many, many years ago by NASA, actually for the space race. It was commonly called carbon PEEK composite. So PEEK is a polymer, thermoplastic polymer. And it's a very high temperature polymer that supports temperatures in continuous use up to 250 degrees Celsius, although at around 150, it starts to be a little bit weaker. That's where it crosses so-called TG, glass transition temperature. And the PEEK material is also highly chemical resistant. So you can expose it to many different chemicals, including, and that makes it interesting here, hydrogen. So we do have a very highly skilled and motivated team, obviously, here in Switzerland, and we have been jumping on the opportunity to think what else can be done. Some of us are having quite some interest in diving and hence gas. And I literally have back in my shelf here a about 10-pound heavy gas encyclopedia that testifies or is a testimony of the fact that gas is important. So in year 2020, just at the brink of COVID, you may still remember that mask thing, which is luckily far away now. So in 2020, we came first on the idea that probably the combination of high temperature, high chemical resistance, high strength, and low weight is possibly what is needed to compress hydrogen. Mm-hmm. So on paper, everything works well, no problem. But as the devil is in the detail, so we started a few first initial development steps where we looked at material compatibility and we looked at how to actually model it, how we could even test it. And then at the end of the day, we made prototypes. So we started with the first prototype. Well, it wasn't too bad. We went up to 500 meters a second, but target is higher. So our last prototype went up to 688 meters per second, which is ways above where it needs to be for a hydrogen compressor. That's really where we start to see it makes things possible. Well, that's just in parentheses, that impeller now is powder, because that's what happens. One of the nice things when you have composite materials, when they fail, they just mash themselves into little powders.
So what is it about hydrogen as a molecule that makes it particularly challenging to compress when you compare it to natural gas, for instance?
Very interesting question. So let me start there with the very, very basic. You all know the periodic system of elements. And when you look at that, you see on the top left, there is hydrogen. So it's really the most simple, most basic atom that you can create or that nature creates. It's basically one proton, very rarely a neutron that goes with it, and an electron going around. Electrons don't like to be on their own. An hydrogen atom will always look for a body, and most of the bodies that they find are other hydrogens. So both of them share their own electron. They get together, they make a molecule. That's a hydrogen molecule. Now we have 2 protons, 2 electrons. In rare cases, you have even 1 neutron or even 3 neutrons, very rare cases. And with that, you would now have a hydrogen molecule. And this molecule has the weight of these 2 protons and, well, neglect the electrons. Compare that to methane. Methane has 1 carbon, which has a mass of 12, 6 protons, 6 neutrons, and the 6 electrons, which again, we can neglect. So now you see that you have a mass of 16 compared to a mass of 2. And that gets really interesting. Why? Because the compression ratio that you can generate in a centrifugal compressor depends directly on the molecular weight of your molecule that you want to compress. So there's a direct relation between compression ratio, the molecular weight of the element that you want to compress, and the tip speed squared. Very important, squared. So if you want to have at a given compression ratio a hydrogen molecule compressed, you need a tip speed which is 2.8 times the one that you would use for methane. And that's what's really making it complicated for this gas to be compressed, because you need that very high tip speed.
Okay. I do like it when the podcast turns into a science lesson. This is great.
I hope you were able to follow.
I was, yes.
Yes.
Now, so my next question is, this is all well and good, but what sort of things does compression efficiency affect? So what problems are you solving by innovating here?
Yeah, in a nutshell, at every stage of a centrifugal compressor, you increase the pressure by a certain compression ratio. The gas is going from the center, the inlet, to the tip where the speed is the highest. And on its way, it's hindered from flowing backwards because now you have a rip being there, plus the rip is pushing it forward and outside. So that's really the simple way to explain how a centrifugal compressor works. For simplicity, let's take the number of 2 as a compression ratio, which in coincidence is usually what you have for methane gas compressors. So in order to bring your gas from, say, 50 bar to 200 bar, that's a 4x pressure increase, and you have a compression ratio of 2, you will need 2 stages. The first brings you up from 50 to 100, and the second will bring you up from 100 to 200. Now imagine you don't have a compression ratio of 2, but 1.2, which is typically what you would find if you were using traditional compressors with hydrogen. If you do the math, you will see that the first 2 stages will bring it to 72 bar, from 50 to 72. So in order to get up to your 200 bar, from 50 to 200, you would actually need 8 stages, 4 times more. And you can very quickly imagine that this turns in a gas plant. It's huge, it's costly, it's massive. That's not what we want to do. And I think the innovation that we've done here is we enabled going back to close to 2 and hence reduce the footprint of a potential hydrogen compression.
And as we think about scaling hydrogen networks across Europe and beyond, what role do you see advanced materials playing in making those networks economically viable?
Yeah, so looking back into human history, we see that materials are always key. If you're the one with the iron sword and you smash the bronze sword of your opponent, you're probably likely to win. And similar thing here, hydrogen is the simplest of all atoms, most abundant, but it's not an easy one to work with. It's very small, it leaks, it loves to leak. It's not as bad as helium, but it's still very bad. And the problem with hydrogen compared to helium is it's explosive. You don't want to go out anywhere. On top of it, it's odorless. So you want to keep it where it is. That means you need seals. You need really good seals. And then it's very dry as a gas. Gases do behave differently when you compress them, depending on which it is. Hydrogen is really dry. Plus, you don't want to put oil in there because that will ruin your fuel cells down the line. So you need to keep it really dry and really clean. And that is obviously an enormous problem for friction and wear. So your friction and wear components, they can't be just what you're using today. You need to have special ones that not only survive hydrogen in terms of chemical, but are also working in the very dry condition. Talking about chemical, so hydrogen is actually chemically pretty active. And the chemicals, they may damage or corrode, if you want to, many different materials, being it metals or also elastomers or plastics. So it's really hard to work with the traditional materials. So you have to check for the hydrogen compatibility all the time. While we can work today with hydrogen, it is not easy. We have ways of doing compression in the piston compressors. And while it's working, we usually have to change components quite regularly, like every 500 hours. A better material will obviously enable a more efficient and more economically efficient compression. And the same goes on. So you have a good seal that you only have to change every several months or even years rather than every week. You have a hydrogen compressor with a centrifugal compressor that allows you to go to a compression ratio of 2 rather than 1.2. All of these together, all these material developments that are happening right now, that companies are investing money to get into the solution, they all are making economically more viable. It's not enabling in terms of you can't do it without, because we have hydrogen, we work with hydrogen today, but in order to have it economically viable at large scale, we are not ready yet. We're getting there though.
You talked earlier about prototypes. What kind of testing is required here? What kind of testing do you need to prove that a component like this is safe, that it's going to be reliable, and that ultimately that it's ready for hydrogen service?
Excellent question. So obviously we need to start with a building block. The material itself needs to survive in that environment in terms of temperature and especially in terms of chemical, in that case, hydrogen. So we have obviously done a lot of this testing, soaking our material in hydrogen for a long time and then testing it in all different kinds and ways, being it tensile tests, compression tests, or all the mechanicals, see if there's any knockdown anywhere. And luckily there is none. So carbon peak is actually a good candidate for that application, a very good one. And then once you have that, you need to have a very good understanding of how you need to design. You don't want to design at the brink of where it's going. People do that. I should say that, but it's true. If you're going in an elevator, you have a safety factor probably closer to 10 because you really don't have to fail. But if you go in an aircraft, you don't have a safety factor of 10. There's a lot of surveillance on the aircrafts because you can't. Otherwise, that thing will not fly. We don't need a safety factor of 10 in these applications, but we need a little bit of safety factor. Not for the actual safety, because as I said before, when it fails, it gives you powder. But because you want to have it reliable, it shouldn't fail in service. So we need to understand how to design the parts. We need to understand how stresses are generated and where and how stress concentrators are generated. And so once you understand that and you have models that can predict these, it's much better, or you're much better suited to actually avoid these kind of limit conditions and getting closer to a more safe or more away from the ultimate limit of the material or the design status. So it's all about making the right decisions for the design to stay away from these extra close events where things could fail at a very short notice. And with that, you're going to have a good design. Now, before you can put in service, in any case, you want to test it. So all these composite parts, they are tested like any impeller actually in a spin test before they go into application. And that's unfortunately quite costly thing. So there are special equipments that are needed to do these tests, and all the compressor OEMs, they would have these.
Super. And if you had to sum it up for a pipeline engineer or a project developer listening to this episode, what should they be thinking differently today about compression when they design hydrogen infrastructure for the long term?
It's a very interesting question. Funnily, around Christmas and on holiday, I did speak to a friend from Germany who is working in the gas distribution sector. And he did even not know that there is a problem potentially. So far, everything was working at 360 meters per second tip speed. And I think most people have actually assumed that this is not a problem in the future for hydrogen. And as we have discussed earlier, given the lightweight, that's not entirely true. So what we have demonstrated here is that it is actually possible if we go into composite impellers to go to your 600 meters per second tip speed, and that the assumption of from above, not the 360 meters per second, but the fact that you can still use the same equipment may be true or truer now than it was a few years back before we have done this development. So today, I would think that for the guys doing the centrifugal compressor design, they have actually now a new speed limit. They have to think about how do you actually make your compressor to run at these quite high speeds. So to say, they need to do a lot of adaptations. The axis, the bearings, whatever is needed needs to be adapted. And for the pipeline guys, obviously, we have now removed one of the roadblocks or enabled it. So keep pushing so that it really becomes reality. We want to have that hydrogen network in Europe and worldwide.
Thanks for being on the podcast, Sam.
Thank you, Elizabeth, for having me.
Thanks to Dr. Sam Stutz at Greene Tweed for teaching us about the new speed limit we must take into consideration when we design and operate hydrogen pipeline transport. Thank you, as always, to everyone in the World Pipelines podcast audience. If you enjoyed this episode and want more, you can visit our back catalogue of episodes. We recently had a trio of episodes focused on cyber threats and digital strategies for pipelines. Plus, we had a whole season on pipeline organizations and how they help push the sector forward. Subscribe for free wherever you get your podcasts. We're busy planning something exciting. On the 18th of March, I'll be hosting the World Pipelines CCS Forum in London. It's a day dedicated to the CO2 pipeline build-out and how we'll make the UK's carbon capture and storage pipeline networks a reality. We'll cover the engineering challenges specific to CO2 pipelines. We'll outline the different demands for integrity and maintenance. We'll provide project updates from each of the clusters, and we'll debate the future of the sector in the UK. The speaker lineup includes National Gas, United Infrastructure, Eni, SGN, DNV, Penspen, and more. Search World Pipelines CCS Forum for more information. We have special discounted rates for members of pipeline organizations, including the Pipeline Industries Guild, IPLOCA, the CCSA, and UCOPA. Thanks for listening.